Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And within that larger playlist, I'm creating little mini-series that deal with the specific experimental design that we're covering. In this little mini-series, we're looking at analysis of covariance, and we're on part 6 of a 9-part little mini-series. And here we're going to look at a balanced one-way fixed effects ANOVA with one covariate. And we're going to just generally develop this model. And as a reminder, the model is y equals x star beta star plus epsilon. So it is a general linear model, but we partition the design matrix and the parameter vector into two pieces that correspond with the ANOVA part and the regression part of the covariates. And so you do that multiplication. And then in part 2 of this mini-series, we developed we added a well-chosen zero and then changed this model to this, and they're 100% equivalent. Now, and what this does is it allows us to develop the structure behind the least squares estimates and contrast and etc. Here, the X matrix, or the piece that's associated with the ANOVA, since we're doing a balanced one-way fixed effects, it's this, a column of ones, and then a matrix that deals with the tau parameters. The beta vector here is mu, tau 1, tau 2, all the way to tau A, because there's 8 treatment effects. The Z, so the covariance, there's only one, and that one covariate is Z star, and then we subtract off the mean, and so I guess technically that should be the mean of Z star. It's the mean of that, so it's what's called a centered variable. And then if you right factor out a Z, we get the identity matrix minus J, which is a perpendicular projection matrix on the column space of ones. It's right here. Now MX is the perpendicular projection matrix onto the column space of X, which is this. And we're going to assume that the epsilon is normally distributed with mean vector 0 and variance covariance matrix sigma squared I. Now, in what follows, we're not going to rederive a lot of the things that we developed in this mini-series one-way fixed effects ANOVA. We're just going to assume that you're familiar with this and then proceed. Otherwise, it makes the video too long. But you can always go back to this little mini-series and look and see what we did. So first, MX, which is the perpendicular projection matrix on the column space of X, which is this, but this column space is not full column rank, and so we have to use a generalized inverse. But if we get rid of this 1, because it's actually part of the column space of X tau, then we can use the inverse, and then it becomes a non-singular matrix. So these two are the same. Now this ends up being what's called a block diagonal matrix, with 1 over n being an n by n matrix, down the diagonal. And of course, un can be thought of as this vector multiplication. So it creates a matrix of all ones. Now mx times z, now remember that this is a centered matrix, and so technically this should be the mean of z star. Then we multiply that in and we get this. Now mx times z is what's called a treatment vector mean. So it creates little pockets. So it's the mean of the ith treatment, or it's actually the z's associated with the ith treatment mean, and there's n of them, and then that goes all the way down to the 8th treatment. And then this is the mean vector, so it's often called the grand mean, and this is the z treatment mean vector. Now I minus mx, if we times z, so we multiply z into that, and then we get this, and perhaps I might just say whenever you see a z dot star, it should have a star there. Then, so this vector creates this. It's a vector of the z's minus the mean, so it's a centered vector, and this we just discovered. Now, this and this are the same, so they cancel. Minus a minus creates a plus, so they cancel. And so we're left with z star minus the treatment mean vector. And then that vector can be thought of as this. It's the individual z minus the mean of the z's for treatment 1, and all the way down to treatment A. Then you're subtracting the mean of the z's associated with the 8th treatment effect. You're subtracting it all the way down. So that's what this creates. Now, I minus mx creates something very similar. So multiply the y in, so we just get the y vector. But this creates a treatment mean vector, and so this difference is this. The treatment mean, of course, there's little constants here, where it's just the mean associated with the ith treatment. Now, z, I minus mx z, since I minus mx is idempotent, it's actually a perpendicular projection matrix, we can multiply it out and it doesn't change it. Then we can sort of untranspose that into this because it's also symmetric. But this we discovered was z star z treatment mean, and this was the same. But then this vector product creates a sum, and so in scalar form this is this. Now, if this is invertible, so we just looked at this, meaning since this is a number, so if this is non-zero, it has an inverse. And if it has an inverse and it's a scalar, you just take it to the bottom. And then we're going to call this SSZZ, 1 over SSZZ. Now this one, Z transpose, I minus MX, Y, we're going to do something very similar. The I minus MX is idempotent, so you can multiply it out and then untranspose this second piece, and we're left with this. But this we developed into this, and this we derived this. And so this vector product creates the sum of the cross products. And let's just call that generically SSZY. So that means the least squares estimate for gamma. And if you look in the, I think it's the 3rd video in this series where we derive the least squares estimates for these parameters, is this. And this we call SSZY, and this one was SSZZ, and it's generalized inverse. And this is so similar to simple linear regression. Now, if SSZZ is not invertible, that means this is not unique, which says that the least squares estimates for gamma are not unique. But if it's invertible, then you can divide by, and it creates a unique estimate for the least squares estimates. And actually in the R software, we illustrate this, and it's actually quite cool, by the way. So now in part 3 of this little mini series, we said that the least squares estimate for beta tilde, has to satisfy this equation here. So this right here. But now let's look at this piece. So if we multiply that in, we get this. But that creates the treatment mean vector for the y, and this creates a treatment mean vector for z. And that should be centered, right? So I'm missing a minus ZGM here. So let's just put it in. Oh, no, that's right. because there's no star here, that's the centered variable. And then that's the centered variable which creates that, what we had on the previous page. So it is correct, and I'm sorry. But what's interesting, and I also illustrate this in the R software in the last two examples, that we create several least squares estimates for beta. And none of them are unique. They're all different. But when we take x times each of those least squares estimates, it's the same thing. It creates a unique vector. All right, well, I hope this helped with some of the theory and calculations and derivations and analysis of covariance. This was sort of a simple example where we look at just a balanced one-way fixed effects ANOVA with one covariate. Now we're going to do the same thing in the next video, but it's going to be a balanced complete block design with one covariate. We're going to do the same thing, and then we're going to, in the last two videos, we're going to illustrate all these concepts in R. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.